Bueno, buenas tardes. Ya estamos en la recta final, ya estamos en el último día, pero eso no quiere decir que las charlas del último día no sean fascinantes. Una, pues es una investigación que llevamos a cabo puntera, muy puntera, yo creo, con la Universidad Politécnica de Barcelona, que es la que les viene a contar el profesor Tous. Y la otra es fascinante porque es el control de calidad de servicios, que la viene a presentar el doctor Anastasius, ¿cómo es el nombre? ¿Cómo? Monchoviu, complicado, de Atenas, que es un economista. Lo que pasa es que especializado en el entorno de calidad asistencial. Ambas son interesantes, de tal manera que espero que sea un buen final de curso. Pues, en primer lugar, déjenme presentarles al doctor Rubén Tous, que ya ha venido en varias ocasiones porque llevamos la investigación sobre las biopsias ópticas y el acceso a la misma para el diagnóstico automatizado. Él pertenece, como habíamos comentado en otras ocasiones, al comité de expertos del JPEG 2000 y al comité de estandarización del JPEG 2000, de tal manera que cualquier propuesta que nosotros hacemos en el entorno del manejo de imágenes, él puede traspasarla o transportarla al comité de estandarización. Pues thank you very much for coming, Professor Tous. The floor is yours, and happy to be here as always.
Thank you. So, good evening, everybody. First of all, thank you, Professor, for inviting me once again. I'm very glad to be here. Let me first start with giving you some idea of what I'm going to talk about. I'm not going to talk about theories, formulas, so on. This is the kind of things I explain at university, but I prefer to talk about a project, and specifically about the results of this project. Basically, I'm going to talk about software project, a program, and the motivation of this project. This project has been developed at UPC, at Universitat Politécnica de Catalunya, by my research group, but also in cooperation with the group of the Professor Ferrer-Roca. The main idea came from here, from Professor Ferrer-Roca, who had the vision of the project, and basically we did the brute force of the project. The motivation is that there is now a novel technology for diagnosing biopsies, which is generally called optical biopsy, which allows to analyze a tissue from the body in vivo without extracting the tissue from the body through a process of surgery. This has amazing advantages, but there is also a problem. The process of optical biopsy generates a new kind of images, and these new kind of images has different features from the typical histopathological images you probably have seen in your lectures. So healthcare professionals dealing with these new images don't know or have problems to classify, to identify, and to diagnose these optical biopsies. Our approach to a solution to this problem is providing these healthcare professionals with a image search system which helps them in finding images, optical biopsies from precedent cases with their related precedent diagnosis. If you can take a look to a precedent image with the corresponding diagnosis, you can improve your confidence diagnosing. So this is basically the motivation. So as you can see, and the solution is not very complex. No, it's just an image search system. But we have a challenge because we want that users of this system don't need to enter keywords or metadata filters to the search form, like, I don't know, in Google or other places. So we don't want doctors having to explicit, for example, I want images for this day, from that place, etc. We want just the doctor taking the example images from the ongoing endoscopic session and inputting it into the system. So this is more complex, and it's related to a research area known as content-based information retrieval, which is my area of expertise, and this is what I'm going to talk you about.
Déjame traducir. Vamos a tratar de biopsias ópticas. ¿Qué son biopsias ópticas? Es una biopsia, es decir, una imagen histológica, pero sin histología. Es decir, tú no la sacas del organismo, tú no la cortas, tú no la tiñes, no haces nada. O sea, simplemente la ves directamente con un microscopio en el interior de la persona. Para esto, pues son microscopios láseres confocales especiales que se utilizan, pues, en endoscopia o en otras tecnologías. El problema es que la biopsia óptica la biopsia es una especialidad de anatomía patológica y diagnosticar una biopsia, pues, requiere años de entrenamiento. En cambio, estas biopsias las ven los endoscopistas, las ven los clínicos, no tienen la más remota idea de la anatomía patológica. Por lo tanto, hacen poco con ellas porque no las saben diagnosticar, a no ser que avisen a un patólogo que venga a ver qué es lo que ven ellos. Sistema. Nosotros le vamos a proporcionar una base de datos en la que ellos simplemente colocando la imagen que han sacado del endoscopio, la ponen en un sistema de búsqueda de imágenes y este sistema de búsqueda de imágenes le busca una imagen exactamente igual o muy parecida y le dice que la imagen que ha encontrado tiene este diagnóstico ya confirmado, benigno, maligno, inflamatorio o lo que sea. Esto es una cosa que parece sencilla porque ustedes van al Google y buscan en imágenes lo que sea y les salen imágenes, pero aquí es que no utilizamos lo que se llaman metadatos, es decir, no ponemos en la cabecera de la imagen ni lo que es, ni a qué enfermo pertenece, ni qué patología tiene este enfermo, ni lo que se ha visto, para que luego la base de datos lo busque y lo saque. Es decir, si ustedes van al Google y ponen imágenes de coche, pues ¿por qué le salen coches? Porque está con el metadato coche, ¿no? Y si le ponen que es de color rojo, pues salen de color rojo, lógicamente, ¿no? Entonces, lo que nosotros queremos es que el sistema sea inteligente, por lo tanto, ya estamos en el entorno de gestión inteligente del conocimiento, en el entorno del Health 4, de 4.0. De gestión inteligente de una base de datos compleja de imágenes. Para esta gestión inteligente, bueno, pues el informático, el programa informático, la persona que lo programa, tiene que hacer muchas más cosas que poner una imagen. Tiene que saber identificar una serie de cuestiones en esa imagen, que es lo que ellos están modelando.
Okay. So, this is the outline of the presentation. First of all, I'm going to give you I will start with the worst part for me, which is the medical part, as I'm not a medical expert, so I will explain a little bit this technology of optical biopsy, specifically one of the specific technologies, which is confocal laser endomicroscopy. Then I will go to my part, which is this content-based image retrieval. I will just tell you some general things and I put some examples because now this kind of technology is used also in commercial applications. Probably you have seen several of them, and I will also talk about smartphones and these kind of things. Finally, I will go to the specific project, and I will show you a small demo of 10 minutes at the end. So let's start with the optical biopsy concept. An optical, as I have told you before, an optical biopsy is a non-intrusive optical diagnosis method. You can obtain an optical biopsy through several techniques. You can do, for example, OCT, optical coherence tomography, stereoscopy, other technologies, but I'm going to focus on confocal laser endomicroscopy, which is first of all, because probably it's the more advanced and mature technique, but it's also because it's the kind of devices that the university which is providing us the images are using, so we have to use it. And the advantages are amazing. No? You can imagine you don't need to go to surgery to extract the tissue from your body, so we are talking about a reduction of costs in terms of money, in terms of time, also an improvement of user experience, patient experience, of course. But it's not that we are only improving the things that we did in the past. The fact is that we can do new things because the optical biopsy is obtained in real time. So with the endoscope, you can go and do biopsies at the same time you are doing the endoscopic session, so you can do new things. You don't need to select the tissue and the region so carefully, so you can do several new things. But the problem is that these are new images. These images you have seen here, this pink one, probably you have seen it several times, is the typical histopathology of a region of the colon mucosa, of the human colon mucosa. This one in gray is the one of optical biopsy. As you can see, they are similar. But if you try to use one of the applications that currently help processing these images, these applications are not going to work with this one. And if you are going to use, because there are established clear criteria to diagnose this kind of image, but if you go to this criteria, you are going to see that they need to be revised in order to be applied to this different image. So we don't have, as you call in your area, don't have a gold standard for optical biopsy.
Aquí ven la imagen de una histología y la misma imagen vista con una biopsia óptica. Ven ustedes que la estructura es exactamente igual, lo único que una ha tenido que hacerse una biopsia, teñirse, procesarse, etcétera, y la otra se ha capturado on the fly, o sea, mientras se está haciendo la endoscopia, se pone en la punta del endoscopio un microscopio específico, miniaturizado, que hace la biopsia. La de la derecha, la óptica, está absolutamente estandarizada por años de experiencia. La de la izquierda todavía no está estandarizada, no sabemos bien cómo diagnosticarla, aunque morfológicamente son idénticas. Y particularmente el problema consiste en que eso lo ve un médico que no tiene ni idea de anatomía patológica. Todavía si lo viera un patólogo, pues todavía diría que bueno, que no se fía porque a él le gusta verlo de la otra manera, con colores, pero bueno, estaría más cerca. Pero si la ve un endoscopista, pues es imposible que haga un buen diagnóstico.
Okay. So now I'm going to focus on explaining you, because it's not my knowledge, so it's just find this in Wikipedia, but I'm going to try to explain it. And it's the concept of confocal microscopy and confocal endomicroscopy, which is the specific technology we are using for these kind of images. The concept is very old. It came from 1957 and was an idea of Marvin Minsky, who find that if you have a tissue, for instance, you can see it's thick. I mean, it's not just a surface, it's something more. It has some deep. And you want to have images from several levels of deepness of this tissue. What you can do is to have a light source and to have an optical detector, a camera or something like this. And then if you where you place the focus of the light source and you place the focus of the camera, this is what is called the focal plane. So changing the aperture of the lens, you can change the place where both focus converge. This is why it's called confocal microscopy. So changing the aperture of the lens, the focal plane will move from the surface to more deep on the surface. And using pinholes, you can see these devices, you can avoid the light coming from other parts of other levels of thickness. So you are going to have a very precise, with a very high resolution of this region or this region or this region on the surface. So this is more or less my idea.
No sé si pueden entender la cuestión. Si tienes algo muy gordo, tú lo puedes cortar en láminas y puedes verlo en láminas, ¿no? Es lo mismo que vimos ayer en la tomografía o vimos pues en la reconstrucción tridimensional. Aquí ni lo cortamos ni lo tenemos digitalizado al completo. Lo único que hacemos es enfocar un punto más en superficie o más en profundidad. Y podemos ir enfocando desde la más profundidad hasta la mayor superficie. Y entonces vamos teniendo cortes virtuales del grosor del tejido a medida que vamos haciendo la endoscopia.
Okay. So this was the confocal microscopy in general. Now, if you take a device applying this technology and you couple this at the end of an endoscope, what you have is this, which is, well, this is just the confocal part. You will put this at the end of an endoscope, so you can use it during an endoscopic session, and you will be able to capture images from different deepness in the tissue. For example, this is the section of the human colon mucosa, and this will be the resulting optical biopsy. Currently, there are some commercial products. There are more than that. We are using Pentax. There is a mistake here. This is the code of the device, which is being used at the University of Mainz, which is the one who is providing us the images. But there are other devices from Cellvideo, also others. I don't know. Probably the professor knows better than me.
Uno de los problemas que tenemos en el proyecto es conseguir imágenes, porque nosotros hemos ofertado a endoscopia y a digestivo aquí hacer un proyecto para conseguir un endoscopio confocal y pues no están por la labor. Entonces hay muy pocos sitios que tengan endoscopios confocales. Uno de los primeros sitios y de las personas más entrenadas en endoscopia confocal es en la Universidad de Mainz, que es el que colabora con nosotros.
So this is just some technical information. I'm not going to enter into the details, but in order to allow you to know which kind of images we are talking about. We currently have 137, which is not too much, I know, grayscale pictures of the human colon, all of them coming from the University of Mainz, thanks to the professor Martin Goetz, all of them from a Pentax device. They have a field of view of around 500 per 500 micrometers. This is the size of these images I'm going to show you. So the resolution is very high. The confocal frames, just to know you how it works, because this device is taking photos all the time. It's not that you press a button or something. So it's not like a video, which is about 25 frames per second. It takes these pictures 1.6 or 0.8 frames per second, depending on the resolution do you want. What about the orientation? They are all en-face views of the tissue at different plane depths. It can reach about 250 micrometers in depth within the tissue. And according to this information, you can see that it allows to see the cellular and also subcellular structure, because the size of a cell is about 130 micrometers, and the resolution is 0.7 micrometers. Resolution in microscopy means the visible distance between 2 points, so you can see cellular and subcellular resolution.
De hecho, claro, a nosotros nos interesa resolución celular, ¿no? Como la histológica, pero realmente se llegan a ver cómo se transportan pues por ejemplo, el calcio o el agua en el interior de la célula con este sistema, en vivo, ¿no?
Okay. So this is the human colon mucosa with the glands. Of course, you know better this than me, but just to give you an idea of what I'm talking about. So the images are en-face images of these glands. These glands are these mountains, for those of you who are not from the medical science. And so it's some kind of slices, and then the result is cutting these kind of mountains. You will have something like orange slices, which are these images I'm going to show you. All are more or less the same. Okay? So, as I told you, the problem is that the professional in charge of taking these images is not a pathologist, it's an endoscopist. And he's going to deal with this kind of images. I have this, here you have three. The first one is a healthy image from the colon mucosa. You can see the crypts of the glands. The cells are these small black things within the crypts. And as you can see, these white things among them are the blood vessels. No? I must say that before using this technique, you need to inject to the tissue a contrast agent like fluorescein or acroflavine. And so this is the reason why this image looks with these areas in white in the middle. This contrast agent decreases its effects through time, so it makes more difficult our task because the same region looks different in different moments because it gets more darker in time. This second image is a malignant one. Well, in fact, as far as I know, it's an adenoma. As you can see, you cannot see the crypts. They don't have uniform distribution in the image. The blood vessels are totally hypertrophiated, etc. The third one is a cancer. It's a carcinoma. As you can see, there is no uniform distribution of the crypts, and all that you can see is blood vessels showing bad behavior here. So,
bueno, entonces lo que estábamos explicando aquí era que las imágenes que ven aquí tienen un contraste de fluoresceína. Se inyecta fluoresceína o acroflavina, la acroflavina tiñe las células y la fluoresceína tiñe los vasos, y entonces identificamos lo que es el tejido vascular interpuesto entre las glándulas y las glándulas propiamente dichas, ¿no? El problema está en que, bueno, primero, vuelvo a repetir, lo ve una persona que no tiene idea de la histología del colon. Y luego, pues, todavía en el lado de la izquierda se ve que las cosas son muy bonitas, son todas redonditas y la estructura más o menos se ve perfecta y todo el mundo interpreta que eso probablemente sea benigno, pero ya el del medio o el de la derecha ya no tiene una idea tan clara de la gravedad que pueda ser esto, de si es simplemente una hiperplasia, un adenoma o ya estamos hablando de un carcinoma, ¿no? Y en cambio eso se puede saber perfectamente.
So the tool I'm going to explain you, it's related to something which you probably know, which is CAT. CAT means computer-aided design or computer-aided diagnosis. Another set of tools normally related to the use of images, but also to the use of audio and so on, which helps physicians doing their job. There are several approaches to CAT, like image processing, segmentation, etc., but the one in which I'm going to focus is the searching for similar images in order to help gain confidence through the process of analogy. This is related to something which is called case-based reasoning, which is not only applied to medicine, also it's applied in law and in other areas, so it's some universal concept. This case-based reasoning is related to a capacity of the human intelligence with it, which is the process of analogy. You know? If you find a similar case from the past, you, by analogy, can see which are the way you have to follow in order to solve your current problem. So what we are going to do is to develop a CAT system specifically for this kind of search of precedent diagnostics, and in order to allow to, given as an example image from an ongoing endoscopic session, to find precedent images with their related information, metadata, from other physicians who annotated these images, so helping you in order to solve the problem.
La filosofía es una filosofía clásica. De hecho, así es como se aprende en anatomía patológica. El patólogo lo que hace es, cuando ve una imagen que no ha visto antes, que coge un libro y empieza a pasar páginas a ver si ve alguna foto que se le parezca. Así es como se hace, simplemente, ¿no? Entonces, en vez de hacerlo de forma tan burda, que verdaderamente es del género ridículo, lo lógico es que simplemente lo ponga una máquina y la máquina automáticamente le pase las hojas, digo yo, ¿no? Entonces, eso mismo es lo que intentamos aquí, pero aquí más complejo, porque estamos pasando de una imagen que teóricamente es histológica a una imagen que es in vivo, o sea, que no está teñida, que tiene otra morfología, que tiene otras características, ¿no? Y, como él dice, eso es lo mismo que hace pues el abogado que quiere defender un caso. Va a ver casos anteriores que se parecen al suyo y dice, mire, si en los otros ha dicho usted que esto es así, pues en el mío, que es igual que el otro, tiene usted que decir que esto es así, ¿no? Entonces, de eso se trata, es decir, de enseñarle al médico, mire, este caso que usted no tiene ni idea, otros en otro momento con un caso parecido lo han diagnosticado de esto y de esto. Ahora usted diagnostíquelo de lo que quiera, es decir, no le damos el diagnóstico, ¿no? Pero le decimos, para que usted sepa, hay 4, 5, 6 casos que son comparables con el suyo y que tienen ese diagnóstico. Y a usted decide lo que tenga que hacer y cómo lo tiene que diagnosticar. Entonces, de esa manera no solo se aprende más rápido, de tal manera que a lo mejor ya dentro de poco este señor ya no necesitará ir a buscar a la base de datos, no solamente se aprende más rápido, sino que además uno se queda más seguro de lo que hace y más tranquilo de lo que hace.
So, this is all for the medical part. And now I'm going to tell you, not about the project, this will come later. I'm going to tell you things about this content-based image retrieval. I have placed here an image of a smartphone because CBIR, it's a very old topic, but now has been boosted or fostered by the fact that by the smartphone revolutions, all these smartphones with these very good cameras allow to take photos from things. So there are a lot of people developing applications. Some of them are already in the market, in which you can, making a photo of something, bring information from this thing for your purpose. So let's talk a bit. I will explain you a little bit about this CBIR concept, and we'll show you some.
¿Me dejas decir un momentito? Él lo que está diciendo que ahora mismo se ha puesto de moda con los sistemas móviles que hay con cámaras tan buenas, de que cuando haces una foto de una cosa quieres tener información adyacente a esta cosa, ¿no? O sea, esto sería lo que se llamaría image enhancement, ¿no? O sea, no en aquel preciso momento, pero buscas en la base de datos información sobre esta imagen, lógicamente. Si tú fotografías en París la Tour Eiffel, pues te da información de quién la hizo, de qué está hecha, de cuándo se inauguró, de cuándo no sé qué, ¿no? Información complementaria, que como dijimos es muy clásico en el entorno turístico. Pero este enhancement es lo que estábamos nosotros proponiendo en el Health 4.0. Es decir, nosotros hacemos una foto de una manzana y nos dice de qué está compuesta, qué características tiene, y si hacemos la foto de todo lo que comemos uno por uno, nos dice, mire, usted se ha pasado de calorías porque el médico a usted le dice que es diabético y no puede pasarse de tantas calorías, ¿no? O sea, estamos vamos a llamarle, en la ola de la modernidad, en el knowledge based, en la base de datos de conocimientos, buscando información adyacente a cosas.
Okay. So, if one of you, I don't know, if some of you will be later interested in finding information about this, I recommend you not to use this CBIR keyword for searching it, because of course you are going to find a lot of things, but now there are new keywords for this. Some people, especially at Stanford, are popularizing the terms visual search, especially for mobile phones, but also in general. This visual search topic is in fact more broad than the CBIR, because it covers two different problems. The first problem, which is the classic one covered by CBIR, is I want to find an image. So, for instance, I can do it through keywords-based image retrieval, for example, using Google Image. No? Another approach is using metadata. This is the typical case in hospitals. They have some forms, and they can say, okay, give me the image I took 1 year ago in this hospital. So this is the typical old case. And then you have this content-based image retrieval, this CBIR, which is our focus here, in which I submit an image and then I find some similar images. This is the classic problem. But now these people calling it visual search have generalized the problem. And the fact what you want is not an image. What do you want is information. And what do you have is an image. So, for instance, this case in front of the tower, Eiffel Tower in Paris, then you are going to take a photo of the tower and you want information. One possible approach is to go to the database, search for similar images, and then extract the information related to them. So, we are again in CBIR. So, this is our case in the optical biopsies scenario. We want information, but we're going to solve it through the search of similar images. But there are other approaches. Through the use of computer vision techniques, you can extract information from a picture without the need of searching similar images. You have object recognition and several other things. This is also related to the augmented reality topic, and all of these have been boosted, fostered by the revolution of the smartphones. I'm going to talk about just this first line, but if you are interested in all these things, I recommend you to visit especially a web page of a research group at Stanford, which is called the Visual Search Research Group, which is now probably the best group in this area.
Bueno, como pueden ver, este es un tema de investigación absolutamente puntero, que ha estado muchos años en el candelero o en los laboratorios de investigación, pero que ahora tiene un interés absolutamente especial. Realmente el grupo de Stanford lo ha cambiado por el término de búsqueda visual. Incluye lo que nosotros hacemos, que es buscar una imagen pues en Google con determinadas palabras, o buscar algo porque tiene metadatos que nos permiten identificarlo, o como nosotros hacemos, buscar algo mirando directamente las características de la imagen, pero también la segunda parte, que es añadir información a eso que buscamos. Y de hecho nosotros estamos en el primer grupo, porque cuando nosotros buscamos las imágenes similares, en realidad lo que buscamos es el diagnóstico que tienen estas imágenes, para que nos ayuden a nosotros a diagnosticar las imágenes que tenemos ahora. O sea que realmente estaríamos en el segundo grupo, pero aparte tendríamos pues la visión de la reconocimiento de la visión por computadora, la realidad aumentada, que es la que les digo de la manzana que les informa del contenido, etcétera. Y todo esto está disparado gracias a la disponibilidad de imágenes de buenísima calidad con los smartphones y el acceso a bases de datos con smartphones.
Okay. So maybe some of you are wondering, well, what about Google? It works quite fine, so I can't find anything there. I can't find images, so what I need anything else? So I agree with you in that almost most part of things you can do them with Google, and it's fast, it's good. But there are situations in which Google is not enough, or things like Google. For instance, in the case of optical biopsies, in Google the search is based in the fact that all the images are surrounded by a lot of text and also metadata, but also normal unstructured text. And so Google exploits this thing in order to help you finding things through the use of keywords, which is the first case. But in the case of optical biopsies, during an endoscopic session, they are not surrounded by text. Nobody is inputting metadata, at least at this moment. So these images probably are going to a huge database in which they are going to get lost, because nobody is never again going to find them, because they have nothing attached to them. So you need something else. This something else is CBIR. And basically, the idea is that the search algorithm exploits the visual information within the image. This visual information normally it's divided in three parts, which is color, texture, and shape. But if there are other things also, if you are interested in finding more information about the classic approaches to CBIR, I have added some bibliography at the end of the slides, also in the proceedings, so you can check them. So the steps of the process of CBIR consists basically in three steps. The first one is the extraction of this visual information. I told you that the conventional approach is to take information about color, texture, and shape. But there are more advanced approaches. For instance, this image is just a virtual image. One can imagine that the extraction of visual features can understand in some way the image and infer that this is a car, this is a man, etc., identifying these objects and extracting the information about these objects. This is not the real case. In fact, we cannot do, well, some people can do this in some special situations, but normally what you can do is just extract the color histogram, some information about the shapes and the textures in the image, and so on. It's important that you select which information you want, because later you are going to use this information to decide if this image is similar to another one. And similarity, despite of the fact that we use it in an absolute way, saying that something is similar to another thing, similarity is not an absolute in a multidimensional space. It's something relative. I don't know. For instance, a red Ferrari, the car, you can say it's similar to a red apple if you are interested in color, but it's not similar at all if you are interested in cars. No? So similarity is relative. So depending in which kind of similarity do you want to perform later, you have to decide which kind of information you want to extract from the image.
Esto es sumamente interesante. Realmente es un problema filosófico. Porque primero tienes que saber qué es lo que estás buscando, ¿no? En qué se basa la similaridad. Todo el mundo dice, todos los chinos son iguales. Mentira. ¿Cómo van a ser todos los chinos iguales? Totalmente. Y los chinos no se encuentran todos iguales a nosotros. Todos los negros son iguales y los negros no se encuentran todos iguales a nosotros, porque todos tenemos el mismo color. Y en cambio somos totalmente diferentes, ¿no? Entonces tenemos que saber buscar qué es lo que interesa para saber la diferencia o la igualdad en una imagen, ¿no? Porque por la misma regla de tres, pues bueno, cuando ponemos la imagen de un chino, pues nos salen 50 millones de chinos que no tienen nada que ver con nosotros. Igual que y eso ya es anecdótico, yo siempre le he dicho a los ginecólogos, cuando enseñan las fotos maravillosas de los niños tridimensionales a los padres que se les cae la baba, digo, mira, pero es que todos los veo iguales. Es que todos los niños son iguales, tienen la misma cara, todos tienen la misma cara, pero los padres ven unas igualdades impresionantes. Es mi hijo, se parece a mí, no sé qué, pues todos tienen la misma cara y cuando nacen los niños todos tienen la misma cara. Entonces, bueno, eso es un problema filosófico y solventar eso filosóficamente muchas veces es el quid de la cuestión de cómo va a funcionar un computador. Por lo tanto, eso es lo que es inteligente por nuestra parte poner dentro del computador.
Okay. So first step is selecting the features, the low-level features. Then you have to extract the features, which is not easy. So even if you have a good selection, you have to develop some algorithms to extract those features, which is not easy. But then, when you have these features, you have to arrange them in some kind of vector, like the one you have here, which is a function which receives as an input the image, is here, and then this vector is a vector of low-level features. It's a quantification of this information you have decided, which you will use to compute similarity among images. So this thing is what we call visual signature. It's some kind of, like the fingerprint of the image, something like this. It's also the same in audio. Probably you have had the opportunity to play with these applications in which you sing some part of a song and the application finds which is the song and all the information, so it's the same. It extracts, in this case, an audio signature of the song and performs the search. So in this case, we are doing the same thing.
Bueno, de esto estábamos hablando esta mañana en prácticas precisamente, cómo los niños aprenden los idiomas. Los niños aprenden los idiomas buscándole la estadística al idioma. O sea, los niños cuando las madres, tanto sea chinas, japonesas, españolas o inglesas, les dicen algo, los niños interpretan perfectamente que les están dando de comer o que les están regañando, simplemente haciendo una estadística de los sonidos. Eso es lo que él ha dicho, la firma visual, que en el caso del sonido es la firma auditiva. Que hay programas que pueden interpretar dónde están las palabras o qué es lo que se dice con la firma auditiva, que los niños lo hacen intuitivamente, así aprenden los idiomas, ¿no? Y que nosotros, pues, que algo que tendría que ser tan intuitivo, pues para explicárselo a un computador necesitamos una cantidad de sustancia gris para extraer las informaciones importantes que la imagen nos da.
Okay. So we have two steps. There are three steps. I'm going to the third now. So now you have the image. You have extracted the features. So you have this vector for all the images in the database, and you are constructing with this what we call the index of the database of images. So when you receive the example image, which you want to compare with all these images, what you are doing is extracting also this information from the example image. And then comes the third stage, which is the search. It's the part is easy from the design from point of view, because what you have to do is just compare pairs of these vectors. So you can use there are several forms of comparing vectors, for example, the simple cosine distance or Manhattan distance, chi-square distance, etc. You have to pick just one of them and then apply this between the example image and all the images in the database. This is the hard part from the point of view of performance, because imagine in Google Images they are dealing with billions of images, and when they show you this results page, before these milliseconds they have compared the image with billions of images and doing this calculation, so you have to do it very, very fast.
Bueno, la tercera parte es que con estas firmas visuales tú estableces en la base de datos un índice y cuando tú le das una imagen le sacas la firma visual a la imagen y la comparas con el índice que tienes en la base de datos, y tanto más se parezca al índice que tienes en la base de datos, pues tanto más dices que la imagen es parecida. Pues entenderán que si lo que pones dentro para buscar es porquerías o garbage in, garbage out, si lo que tú pones es una porquería, la asignatura visual, la firma visual que tú has extraído no tiene valor, pues lo que sacas no tiene valor, ¿se entiende?
So, these 3 steps are the basic idea of CBIR, so I'm not going to enter in more details. If later you want, I can explain you more about distance measures, similarity measures. So let's go to talk about the challenges. Just this is a silly example, but the challenges of CBIR are 2. First is the sensory gap. This is the difference between the real information that is in the world and the information you can capture with your technology. Normally, it was the problem in the past, but now with this confocal laser endomicroscopy, this sensory gap is not a problem at all. So we can obtain all the information we want. Even our optical devices can capture information that the human eye cannot, so this is not a problem at all. But the problem which is not solved is the semantic gap, which is the difference between the information that a computer can extract automatically from an image and the way a human interpret this image. For instance, if I ask, a lady if which one of these 2 guys is more attractive or beautiful, I don't know the answer, but depending on the lady, probably, she will say this one or this one. If I ask a computer and I try to design a program which automatically decides which one is more attractive, I don't know. It's very difficult. It's impossible to do. Probably the computer can use some kind of heuristics, for instance, saying that this one is younger, this one has a more tanned skin, and saying, okay, this one is more attractive. But if you ask probably to a lady in the right side of politics, she will say that this one is more attractive. So it's impossible that you can design an algorithm to decide these kind of things. This is the semantic gap. It's something subjective, so you cannot solve it.
Es obvio que desde el punto de vista computacional los aparatos sensoriales hoy en día pueden captar de todo. Pueden captar calor, frío, temperatura, sustancias químicas, imágenes de múltiples detalles, cosas que incluso ni la visión puede captar, ¿no? Ondas electromagnéticas, miles de cosas, ¿no? O sea que desde el punto de vista sensorial estamos muy hacia adelante, pero el problema se plantea en lo que es el gap semántico. Las cosas son subjetivas, cada uno las ve según sabe verlas. El ejemplo más claro precisamente es el de diagnosticar en anatomía patológica o en medicina en general imágenes, ¿no? O sea, a un estudiante de medicina se le enseña una radiografía que tiene una patología y no la sabe ver. Y en cambio la patología está allí. O sea, no es que no esté la patología, es que no la sabe ver. Cuando ya está entrenado la sabe ver, ¿no? Entonces, pues este es el problema fundamental, las cuestiones subjetivas de visibilidad que no puedes tú capturar, ¿no? Como es el caso que decía de aquí, si en la computadora considerará más atractivo uno que otro, atendiendo de si es más joven, tiene la piel más fina, pero pues una persona de derechas es obvio que considera más atractivo a Rajoy que a Zapatero, o una persona de izquierdas, pues también puede ser obvio que considere más atractivo a Zapatero que a Rajoy, ¿no?
Okay. So, classical CBIR has now an impact on commercial applications. Probably the more famous one is Google. Well, it was something which was called Google Image Similarity Search, which was a beta Google application from Google Labs. Some months ago, it's very recent, Google has promoted this application to their Google Images application, so now there is no more Google search, image similarity search, so you can find it just integrated in Google Images. So if you right-click one of those apples in the image, you will have the option to search for similar. Probably this is not very useful, this is just my opinion, to start a search, because if you want to find an apple, just press insert apple in the keywords. But once you have found an image which fits your interest, then maybe searching for similar images can be helpful in the sense of having other ones not mixed with other stuff. So it's some kind of good second step in a search process.
Antes Google tenía en Google Labs un apartado que era Google búsqueda de imágenes similares. Ahora ya Google lo ha integrado totalmente en el buscador de Google, de tal manera que cuando en imágenes uno está buscando en la parte de imágenes de Google, clica en una de estos iconos, el Google automáticamente está buscando imágenes similares a la que ha clicado.
Okay. There are several other examples. I'm going to show you just some of them. Oops. Come on.
A mano. Es que a veces se dispara esto, nos ha pasado ya varias veces, Si no, luego lo tienes que hacer con la mano porque se te dispara.
Another example is Gazopa, just an example. It's unspecialized in CBIR search. In principle, it should be better than Google because it's just for this purpose and they offer more things. But if you try it, at least in my case, all the times I've tried it, it's very slow comparing to Google search, so probably you are not going to use it and it's going to be a failure, but it's just my opinion. There are other ones. For instance, this Visual Search Lab from ID offer professional services for people who wants to prevent their images with copyright to being used in other places. You can send an image to them and they constantly scan the web and trying to search similar images. They also scan printed magazines in all the world in order to find if there are somebody else who should pay you something because they are using your copyrighted material.
Estos son nuevos negocios que aparecen, ¿verdad? No se me había ocurrido nunca, ¿no? O sea, está muy bien, ¿no? O sea, gente que tiene imágenes de copyright, ¿no? Imágenes fotográficas y que no quiere que nadie se las copie ni las utilice, y si las copian las utilizan, pues tienen que pagarle royalties, ¿no? Y entonces contratan a esta gente, a la gente ID, a las que pagan mensualmente para que hagan permanentemente una búsqueda en los periódicos, en todo el internet, etcétera, para buscarles imágenes que se parezcan a las suyas, y si las encuentran, pues entonces se supone que les exigen que paguen royalties. Está muy bien.
There are other examples, some of them probably you know most part of these examples. This one is like.co. It's a shop, an online shop where you can buy things using similarity search. I don't know, if you like these shoes, then you ask the system to show you similar shoes, and I don't know. I have never used it, but it can be useful also. Here, let me finish and then. Here I have placed some logos of some in the left side of the slide. You have seen some logos of companies using this technology. There are several others. And in the right side, there are logos of research projects also using similarity search with more advanced features. For instance, I have been using the last years this Caliph and Emir. They even don't have no logo, so it's just in plain text. GNU, Simba, Alpir, Fire, etc. So, but most part of these projects are now going to the commercial side. So it's not the classical approach to CBIR it's becoming not a research problem, just a business opportunity.
Sí, ahora la filosofía del content-based image retrieval, o sea, la búsqueda de imágenes por su contenido, ya se está transformando en un negocio.
Okay, but the real business is now in smartphones and other mobiles. Here in the top, I don't have a smartphone, so I cannot I have not the opportunity to check this, but this application from Google, which is Google's, in which you take a photo from something and it shows you some Google results about the information about this. Is this visual search we were talking about. There are other applications. For instance, you can make a photo of a product in the supermarket, and reading the barcode, it will show you, I don't know, the ingredients of the product, comparing the price with other places, etc., etc. And also, I don't know, you find that somebody is reading a book in the metro, then you make a photo of it and it shows you where you can buy it, things like this. What about medical imaging? This is another history. If you try to make a search of an image like this one in Google search, probably the results are going to be all the same, because probably, I don't know, if you want to find images of a healthy bone, it's not useful to search using color, texture, and shape, because all healthy bones and also broken bones have the same shape, texture, and color. So we need a totally different and more complex approach for the medical imaging. Despite of this fact, there are very good projects working with this. This one is from the IRMA, Image Retrieval for Medical Applications project. They have a very amazing page, so you can visit it if you are interested in something like this. The conclusion is, regarding medical imaging, is that you need a specific algorithm for each kind of image you are dealing. You have a specific algorithm for bones, I know, for the tibia, you need a specific algorithm for the optical biopsy of the colon mucosa, etc., etc. So it's an open problem.
Lo mismo está ocurriendo ahora, no tan avanzado, pero la misma filosofía se sigue en el entorno médico, en la que se busca imágenes parecido a lo que se hace en un Google. El problema lo constituye en que dentro de medicina las imágenes son muy parecidas entre sí, o sea, los huesos pues todos tienen el mismo color, la misma forma, etcétera, etcétera, y entonces es complicado encontrar imágenes parecidas. De hecho, en medicina se tienen que buscar otros parámetros de semejanza y individualizarlos, o sea que tú no puedes buscar un hueso, sino que tendrás que buscar o la tibia o el fémur o lo que sea específicamente y con otros parámetros que sean más específicos y no genéricos de la imagen.
Okay, so we have finished with the first two parts, this part regarding confocal laser endomicroscopy and CBIR, which are the general concepts. Let me now explain you some details, not very technical, about this project, which now we have almost finished. We have a prototype. We don't have a commercial product, but we have a running prototype. Later I will show you a small demo. We call now it BiopSearch, but it's just an internal name, so don't pay too much attention to it. This is a screenshot of the system. As you can see, it's a typical image search system. You have here the keywords search. In fact, this is the client. I mean, we have a very good server with all the technology and so on. And then we have a graphic client, which is a web client, which now we are porting to the mobile environment to use it in the smartphones. We still don't, I cannot show you this because it's not finished. And this client, it's not very good because it was just programmed by a student of the last year, so you cannot expect too much about it. The system offers the three kind of search you can do. It's keywords-based search, metadata filtering in advanced mode, and CBIR. And you can even combine the three things. So this makes the system very complex to design and very special, because you can find systems offering the three things separated, or maybe two of them but not three things, and combining them in such a complex and expressive way. I made a demonstration of the system about 1 month and a half ago in Tokyo, just before the earthquake, just to show you that it's something relevant in terms of research and advanced research now. And it was well accepted by the JPEG. It was in Tokyo in the JPEG plenary, in the JPEG meeting. So that's the case. Then I don't want to bother you with technical details, but just to allow you to make a very clear idea. This is the architecture of the system. It starts when somebody makes the work of taking all the images from a doctor, for instance, these images from the hospital of Mainz, and index them through this process of CBIR I told you about before. Then comes some user with an image, then ask for some query. This query can involve keywords, metadata, the image, etc. Then we use a standard technology, which is this MPQF, this arrow here, which is an ISO standard, an MPEG standard for expressing user queries for multimedia search. Then we use a technology for solving the textual part of the query. We use Lucene. If you are from computer science, probably you know this project, which is for Java programming. And then we combine the Lucene work with our algorithms for CBIR, and then we bring the result to the user.
El esquema es, nosotros introducimos en la base de datos un montón de imágenes previamente a la que se le han extraído una serie de parámetros que, bueno, en realidad la firma visual, y viene una persona que tiene una imagen y quiere consultarla contra esta base de datos, se hace una consulta siguiendo el estándar de MPEG, el MPEG Query, se pone en un sistema de búsqueda que está estandarizado y que es open source, que es el de Lucene, y mezclado el sistema de búsqueda del Lucene del MPEG Query junto con la huella visual, se extraen las imágenes.
Okay. So, as I told you before, the process of image analysis, which is probably more advanced or complex in this program, starts with an image. You extract some features and you construct this feature vector. So here you have I think there are 11 features we have selected for finding the similarity among optical biopsies of the human colon mucosa. They have proven to be at least enough for our current purposes. They have been able to discriminate images which are healthy from images which have adenoma and also carcinoma. So more or less we have a very promising results for the moment. So all these features, I don't want to enter into the details, try to capture basically if the crypts from the glands are uniformly distributed among the image. For instance, we have some kind of coefficient about the silhouette of the crypts in order to know if they are circles or they are something more anarchic. We have something related also to roundness, to border size deviation. We use some statistics like deviation, etc., just to see if they are uniformly distributed. And so this has been the result.
Esto es básicamente los patrones que se utilizan para identificar las imágenes, que en el fondo lo que están buscando es que si estas criptas que estamos viendo están regularmente distribuidas o están irregularmente distribuidas.
Okay. So before you can extract these images, now I'm going to tell you some hints about the algorithm, how it works. You need first to simplify the images, because the images have some high resolution for this kind of application, so there are too many pixels here, so we cannot spend all life trying to extract the feature here. So first of all, we downscale the images, we apply some equalization algorithm finally to reduce the levels of the grayscale levels and to simplify the images and the image information. Here you have the 4 different cases. First, a healthy tissue. This is also, the second one is a healthy tissue but with less fluorescence, so could be the same image but some minutes later. This one and this one are malignant ones. I'm not sure if they are adenomas or carcinomas or whatever. And these are the images which actually we are using for extracting we are not using starting from them, we are starting from them to extract the features.
Las imágenes que nosotros obtenemos tienen que estar simplificadas, porque nosotros no vamos a utilizar cada uno de los detalles, de los altos detalles que nos da una imagen microscópica. Las simplificamos al máximo en blanco y en negro o muy pocos niveles de gris, y son las de abajo las que utilizamos para identificar.
So then we apply the algorithm. I'm not going to give you all the details because the algorithm is very composed by about 5-6 different steps. The main step, for those of you who are from computer science, is a texture invariant, which is the local binary pattern, which is a very typical algorithm for extracting information in texture-based things. And at the end, what we have is that the algorithm shows us which are the centers of the crypts of the glands and tries to highlight which are the glands and separate them from the inter-crypt distance in this way. So this is the information which serves later to obtain these features. So this is the result, these green areas is the result of the image analysis algorithm we are using.
Este es el resultado del algoritmo de análisis de imagen que se utiliza.
Okay. This is a screenshot of our application. Later in the demo you are going to see how it works, but one of the features is that it allows you to know how it works behind the scenes, showing which are the crypts of the images before the search process started. Okay. So let me show you just two examples of the results of the algorithm. For instance, if you input this image of a healthy tissue into the system, these 5 other images are results. The interesting thing, as you can see, all of them are healthy also. If you have used only color, shape and texture descriptors, you are not going, for instance, to retrieve this very black image, because then the color is very different. But because we are using these specific descriptors for this kind of image, measuring the intercrypt distance, the roundness of the crypts, etc., the algorithm can infer that this image is similar to this one. This is the key of the thing.
Aquí ven, por ejemplo, se ha puesto como consulta la imagen superior de la derecha, y todas las imágenes que nos devuelven son las imágenes que nos dicen, además, porque ya están diagnosticadas dentro de la base de datos, que son normales, que es una mucosa normal.
Okay. So, just to show you an example of a malignant one, if you input, I think this is a carcinoma, if I'm not wrong, if you input this image about a carcinoma in the system, these are the results. As you can see, the results are very different in color, texture and shape, but the system can infer that the distribution of the crypts are anarchic and the blood vessels are hypertrophied, etc., etc., so these images are similar. You cannot obtain this kind of result with Google Image or something like this. Okay. So, this is more or less all I'm going to tell you about the system. Just probably you are wondering which is the performance, how many images you can have, because I told you that we only have 137 images, so you can say, okay, it's very easy, you can take a lot of time for each one of them, etc. What we have done is to artificially multiply these initial images with some transformation, copying them, etc., and we have used 4 different databases with 4 different levels. A small one of the original 137 confocal laser endomicroscopies, then one of 13,000, one of 1 million, and finally one of 13 million confocal laser endomicroscopies, which are not real ones, but they serve to measure the performance. The result shows, this one is in logarithmic scale, shows that even in the worst case, every one of these lines shows a different kind of query, but you can just focus on this green one, which is the Manhattan search, which applies a Manhattan distance for computing the similarity, shows that even, and this, in this coordinate you have the milliseconds. You can think that a search don't take more than, I don't know, 1,000 milliseconds, something around this. But even in the worst case, you can see that the system in the extra large system, it can do it. I mean, it can do it with 13 million images. So the performance is very, very, very good for a medical application. Probably not for Google search, but just for a medical application.
Ellos han simulado 3 tamaños de base de datos. La de arriba es la que se tiene. otra que es de 13.000, de 1 millón y de 13 millones, y han comprobado la rapidez de búsqueda de estas imágenes en la base de datos y han visto que los resultados son muy aceptables.
Okay, so that's all for regarding the design of this BioBserve system. If I have time, yes, I'm not going to spend too much time, but always Professor Ferrer asked me to try transmitting you the importance of standards. Probably you already know the importance of them, but because a big part of my work is devoted to standardization, I will tell you some things about the standards. We are using standards in this project. I'm going to tell you something. In fact, my work and the standards we are using in this project are just from 2 working groups from ISO, specifically from ISO, the joint committee between ISO and IEC. And these numbers don't sound nothing to you, this working group 11 and working group 1, but you use their work every day, because the working group 11 is MPEG and the working group 1 is JPEG. So probably you are using MPEG videos and JPEG images during all your life. Okay. So this image is from a plenary. Is the place where all the people in a meeting, for example, this is a plenary of MPEG, meets, then they split into small groups and discuss different things. This joint technical committee between ISO and IEC is the JTC1, and it's different from, well, it's something which happens also with other ISO things. It's not based in the balloting and the votes and so on. It's not based in companies. It's based on nations. I mean, Spain, for instance, has 1 vote, the same that the US. So in principle, it's in some way democratic in this sense.
Déjame. Ya saben ustedes que nosotros le hacemos mucho hincapié a la estandarización, ¿no? En este caso estamos hablando de estandarización de imágenes, multimedia, fijas o en movimiento. Ellos pertenecen a 2 comités de estandarización, al 11 que hace las imágenes en movimiento MPEG, que todo el mundo conoce, de los vídeos, etcétera, y al comité 1 que hace la estandarización del JPEG, que también todo el mundo conoce, con las imágenes estáticas, ¿no? Incluidas las de JPEG 2000 que han visto de búsqueda de imágenes que se mueven y que puedes desplazar dentro de anatomía patológica. La discusión de cómo evoluciona el estándar y cuáles son los elementos que se tienen que introducir en el nuevo estándar, pues depende de la votación. Ahí han visto imágenes de las sesiones plenarias. La votación es democrática, pero no es individual ni por grupos. No están representadas las empresas y solamente están representadas las naciones. O sea que cada nación tiene un voto.
Okay. So, in the JTC1 committee, there is a subcommittee which is the 29th subcommittee, and in this subcommittee there are these 2 groups which are the working group 1 and working group 11, which are JPEG and MPEG. In the old days, it was first JPEG, and then they decided to split it when the videos appear and so on. If I don't know, if some of you in the future work in a company or maybe now you are working in a company and you are interested in participating in these meetings, they are open to anybody. The only thing you need to do is go to this company, which I know probably you know it because it's the organization in Spain with responsibility in terms of normalization and standardization in all the areas. And you have just to send your CV, your curriculum to AENOR, and if they decide you are an expert in your area, they will allow you to go to this meeting and then you to participate. So it's very open. If you want more information, I recommend you this web page in which you are going to find everything. Okay. So I'm not going to tell you more about this, but just to let you know that JPEG meets three times a year and MPEG meets 4 times a year. They say that these standardization groups do not exist between the meetings, so they only exist during these 4 meetings a year, 3 meetings a year.
Is that true?
Is the truth. Anything you do between the meetings is not official. I mean, the only thing official are the one you do during the meeting.
Okay. Dice que los comités de estandarización no trabajan entre las reuniones y el primero, el del JPEG, tiene 3 reuniones anuales y el del MPEG tiene 4 reuniones anuales. Cualquier cosa que se diga, se comente entre las reuniones no tiene valor ninguno, solo tiene valor lo que se admite y supongo se vota, ¿no?
Exactly.
En las reuniones, en las plenarias.
Okay. So, just to give you 2 examples, I'm going to use the 2 things we are using, which are standards, and we are using them in this BOP search project. The first one is this MPEG query format I mentioned you before. I'm not going to give you details, just to show you an example. If a user enters a query, for instance, give me images showing a colonic lymphoma, images who were taken in 31 of December of 2009, for instance. Then you can compose this query, which have some keywords and some metadata filter, which a Boolean tree. But also you can have more complex query, for instance, one combining this metadata filter, I want images taken the 31 of December of 2009 with an example image, which is this one, and then you also have a Boolean tree. This is more or less the general case. So using the MPEG query format, which is a standard, you can translate this user information need in this kind of XML document, where you can see there is a tree where all the image, for instance, the condition about the date is here, and the condition about the similarity is here. In this case, I used a base 64 encoding for encoding a very small image. Normally, you are not going to use this. You are going to use just an URI, an identifier of the image, something like this. So this document can be understood by any kind of system which is exposing an MPQF standard interface. So this way, anyone in the world who wants to connect to our system can just go to the standard and take a look how to do it. So this is the good thing of using a standard. And the second example is related to the metadata. We are using this JPEG standard, which is called JP Search. It's almost finished. MPQF is finished, but JP Search is ongoing, but it's almost finished. It allows you, for instance, to encode the metadata of an image in this way. These are fields of the JP Search metadata schema, and they do it in a way that you can embed, you can put within this descriptor metadata from other formats like DICOM, like MPEG-7, etc., etc. So if you annotate the images with this kind of thing, your images can be understood anywhere, anytime. So it's a good thing.
Aquí tenemos 2 ejemplos de estandarización. La una es la estandarización MPEG, que ya está terminada, y la otra es la JPEG, que casi está terminada pero está todavía en funcionamiento. 2 formas de establecer el código fuente, código que es XML, como pueden ver, o sea, que se puede leer perfectamente y que está disponible en el momento que haces el query.
Okay. Now I have finished the presentation. Now I'm going to show you a 5 minutes, 10 minutes demo. So it's going to be very fast. I must say it's not too much amazing because it's just a prototype. But okay, we have a link to it we have a link to it on the web page. This is you have seen also the screenshot. This is the main page. You have the images. This is the typical Google way of showing things. You can increase the size of some images. Here is a mix. This is an arbitrary, aleatory selection of healthy and non-healthy images. You can select one image, pressing this select link, then you will see the metadata. This metadata come from, this is a JP Search metadata format. These things are because the video has some problems, but it's just going to happen now, I think. So you can see this is probably it's very small, but this is the same information I showed you before, saying when the image was taken, etc., etc. So we offer also some editing tools for, I don't know, a hypothetical doctor using it, for example, a magnifying glass, something We have also a zooming and something to measure the distances within the image, for example, the creeps, the intercreep distance, things like this. We all allow to crop a region of the image. You can, once you have cropped the image, you can use this region to search similar regions, etc., etc. Then let's do a simple search. You can do a keywords-based search, for example, searching for carcinoma. In this case, it's easy because all the images have been annotated with metadata, so you can do it. So you can search for carcinoma, so you don't need to go to a slow similarity search. So you have seen all of them are carcinoma. If you search for normal images, it's the same case. You have seen here healthy images in the database. As you can see, there are not too much images. And we offer also metadata filtering, which is advanced, and there are normally commercial products do not offer these kind of things. But if then let's refresh it with, let's select this healthy image. Then we offer the possibility to the user, this is something only for the prototype, to run the algorithm and see which are the creeps highlighted by the algorithm. We are going to remove it when we deliver a more commercial thing. The application shows the feature vector with the values, which is something useless, totally useless for a normal user. And for instance, let's do a similarity search. Let's select this one and search for images similar to this carcinoma. As you have seen, it's similar to the example I showed you in the presentation. All these images are malignant ones. They show different shapes and colors, etc., but they have been detected by the system. If we apply the algorithm for extracting the features here, you will see that the creeps are not uniform. They are totally anarchic in the picture. So I think this is all. Okay. So, thank you.
Thank you very much. Bueno, han visto realmente una aplicación funcionando en la realidad. Esto es sumamente útil. De hecho, la gente tiene miedo de utilizar la endoscopia, la microscopía el microscopio confocal en endoscopia precisamente porque tiene miedo de interpretar las imágenes. Si nosotros le damos una herramienta que lo ayuda, que lo deja descansado, de decir, bueno, esta imagen me parece que es maligna, busco en la base de datos y me dice, no, despreocúpate porque esta imagen, todas las que se parecen son benignas. Bueno, pues ya me quedo más tranquilo, ¿no? Eso no quiere decir que ahora que todavía no hay experiencia, pues a lo mejor no le haga la biopsia también, ¿no? Pero de momento él descarta una cosa grave o algo maligno en un momento determinado. Así es que la aplicación nosotros creemos que tiene un valor extraordinario. El problema que tenemos en este momento es conseguir una base de datos suficientemente grande como para establecer el algoritmo necesario, porque la gente no tiene imágenes. ¿Preguntas o comentarios? ¿No? Nadie se atreve a preguntar o comentar. Yo creo que nos hemos quedado todos alucinados. Yeah, one question. Good. Yeah, just 1 second that we come with the...
What I'd like to ask is the following. Do you have any experience concerning the implementation of your system with respect to the healthcare professional? Meaning that you have a system which is an information technology system, okay. What about the other part of the equation, the healthcare professional? What are the views of the healthcare professionals dealing with your system?
What is the vision, sorry again?
The views.
The use.
Views.
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 Of the professional people.
Yeah.
I mean, how is the professional
people viewing that?
You have a system. The system has not been implemented in the healthcare sector. No. Do you have any idea concerning the views of the doctors, nurses, the healthcare professionals in general?
Yeah, the problem for me, I'm not from the health sector, so what we are doing is we are solving a problem who somebody from the health sector asked us to solve. Now we are returning the result to them, and we want them to decide how are they going to use it, and then we can improve it. But we need the feedback now from, for instance, this system now is in the hands of this Professor Goetz from the Ment University, who is the generator of the images, and also in the hands of Olga. And so we are expecting from them, they use the system and decide how it fits in the professional proceeding of somebody. So it's not something I cannot ask, because I don't know. I mean,
no, as I mentioned, the problem is that the people is not happy with the technique, because it's out of his training. You know, these are endoscopists, and whatever they see is on their pathology point of view. So they have to ask the pathology to come down in order to interpret whatever is in there, and the pathology is not happy also, because whatever they see is not what they see under the microscope. So no one is happy, but the tool is wonderful, because you do a biopsy without taking a biopsy. So what we try to do is speed up the training of both. Speed up the training of endoscopy in a field which is not trained, which is pathology, and speed up the training of pathology in a field which is not trained, which is endoscopy. You understand? Yes? Yes, sure.
I'm sorry for my way of dressing today, but I was actually walking from downtown here.
Walking, yeah.
I'm working actually in this field of computer-aided diagnosis in mammography, and also in the dermatoscopy. What in fact has to be done later on with the system he presented today is, of course, studies with the physicians. And actually you have to compare how the physician performs without the system to how he or she performs with the system. And we are talking about studies which are in the microscopy, probably similar size than in mammography. And this is studies with 10,000 plus patients. I'm not absolutely sure how it is in microscopy, but these studies, phase 4, after the product is on the market, are normally very big studies. So, and this is to come, and probably in a couple of years we will start to do that type of studies, because this is a very new field.
Yeah.
In mammography we're doing that since 3 decades, so it takes a long time to get to the point you asked about.
Yes.
But the issue in this field is that there are only 3-4 people in the world trained to make the diagnosis. And you cannot expect that everyone in the world will come to these 4 places in order to get trained. You understand? And the tool is very easy. It's just you use the endoscope with a tip which is a microscope, that's all. Therefore, if you have a tool that helps you to get trained, improve a lot. The endoscopists do the same. I mean, when you do minimal surgery, you have to get trained into a center that already have been trained. But in there, the view you have is macroscopic, so it's more close to the surgeons. But the view you are having in here is microscopic, which is very far from the endoscopic training.
But the other way, what we have been introducing is scientific literacy. Okay, and you have to bear in mind that you change many variables concerning daily practice. So in order for all these systems to be applied in the daily practice of the healthcare professional, either doctor and nurse, we have to bear in mind both sides of the equation. It means we have to bear in mind the side of the information technology, but the side of the daily practice as well. It means that if you construct in a way something which is not used by the healthcare professional, that's not valid.
Yes, I can say something, but I mean, you are talking about future steps, and I agree with them totally. But now our work, because if we want that physicians taking their time to do these studies, we need first to seduce them, to make they think that it's useful from the beginning. I mean, before having the studies. So in order, if you want to seduce these guys from Maine to start with this kind of studies and statistics, first they must think that this is some value on this. So this is the stage in which we are now. Now trying to seduce some people around the world for trying this, then let's move to the next step, and then, because we are very, very beginning, but I agree totally.
Yeah, but if I understood the question, there is no question of the interest of the people on using that. There is no question about that. Of using endoscopy, not the training system, using the optical biopsy. There is no doubt. But training, it's complicated because they have to go to only 4 places in the world, and they have to be there, and they have to spend, and this is what is hard.
Then you go back to the question of changing the curriculum of, let's say, the studies doctors follow, nurses follow. So I'm not going to elaborate further because that would be the topic of my presentation, I think.
Okay. Good. Thank you. ¿Preguntas o comentarios? ¿No? Yes?
Usted dice que no hay ninguna duda en el interés de la gente, pero, o sea, parece una técnica tan golosa, ¿no?, tan fácil, que no solo orientado al endoscopista de digestivo, en una era donde todo el mundo se pelea por hacer la cirugía laparoscópica y todo esto, incluso puede ser un campo bastante bueno para el radiólogo intervencionista, ¿no? Pues, se ve la técnica muy fácil y puedes evitar mucho trauma también al paciente.
Claro, pero el problema es de que ellos se encuentran incómodos en el diagnóstico, porque el diagnóstico es histológico y ellos no están entrenados, ¿entiendes? Entonces, lo que decimos es, para entrenarse en esto, tienen que ir a determinados sitios, pasar muchísimo tiempo, porque tienen que hacer un entrenamiento de anatomopatológico en una cosa que no es anatomopatológica, porque la ven en blanco y negro, porque nosotros los vemos con colores y es mucho más bonito y se ve mucho mejor. Entonces no se encuentran contentos con los resultados, ¿me entienden? O sea, le resulta peligroso para ellos. Es decir, ¿por qué van a hacer una técnica cuando les resulta peligroso y no lo quieren hacer? Lo ven clarísimo, pero ¿dónde se entrenan? ¿Cómo se entrenan?
Pero incluso eso, estamos en la era de la multidisciplinaridad. ¿Por qué no puedes tener un anatomopatólogo también cerca?
No hay, los anatomopatólogos les cuesta muchísimo ir a los sitios porque tienen muchísimo trabajo, es decir, ya tienen bastante con lo que tienen. Si les llaman endoscopista para estar allí todo el día mientras están al lado del endoscopista, dice que no, y el endoscopista no tiene capacidad de contratar un patólogo para su servicio.
La telemedicina.
Bueno, esa era una de las razones por las cuales se tenía que hacer tele aquí, es decir, para consultar tú tenías que enviar la imagen al patólogo para que el patólogo diera su opinión. Pero el patólogo también se ha de entrenar a ver estas imágenes. Quizás requiera menos entrenamiento, pero también se ha de entrenar. Entonces, por eso queríamos solventar el problema. De hecho, la base de datos que ha presentado él solo ha presentado la endoscopia, pero la base de datos es mixta. O sea, cada caso tiene el diagnóstico endoscópico y el gold estándar anatomopatológico. Es decir, cada caso tiene que tener la imagen anatomopatológica y la imagen endoscópica. ¿Ya?
Coming back to the evaluation or validation of the method, could you say something about the study design to actually assess the reliability, the reproducibility?
Yeah.
The gold standard is probably the real biopsy, right? So is there any studies out there? Or what is a proper study design to come up with such validation?
Yes, I think because the evaluation method has been designed by the professor, so it's better that she answer the... We
don't have enough cases. We only have 130. Yeah, and the problem is that we cannot, I mean, it looks promising, but we cannot talk of because there are not sufficient cases, and our problem is to increase our database. And particularly, maybe we could increase the database of the microendoscopy. But the gold standards, because we have to have both. We have to have a pair. We have to have the endoscopy plus the gold standard for sure. Otherwise, it's impossible to assure that you have arrived to a good result. And the second, the pathology images are very difficult to get together with the endoscopy. So we are looking for having place, and the problem, there are very few places in the world, and all of them are very reluctant to keep the images. One issue which is very important, plus the fact that even if they want to give you the images, since the images are not structured, because they are not structured in an interesting and good finding database, I mean, they are just collected into the hard disk, there is no way to find out where the images are and which are the good images. This is amazing. It's very complicated. We want to, but it's very complicated. Still, we have not arrived to the...
let me just complement with more technical. According to these limitations, what we have done in this case with this small set of images, we have asked the physicians at the main university, they have annotated the images with the diagnostics, so we have just compared the result of the algorithm with the result of this. And their annotations was just a small classification of, I think, 4 different cases. And so we have computed the precision and recall of the system, which is very good, but it's very small test suite, so it's just to have to feel some confidence that it's working at this stage, but of course we are aware that we know something else. So
and we are looking forward to have more images. More questions? No? Okay, so we 15 minutes relax and we continue with the next. Thank you.